Alright, our topic for this video is implicit differentiation, and you've done a lot of differentiation. You know how to take a bunch of derivatives, and this is a new style called implicit, and let's first talk about what that means and why we need to do it. Not every relationship of x and y points is a function. Here's an example. This circle has the equation x squared plus y squared equals let's see, the radius is 5, so 25. It's a circle centered at the origin with a radius of 5. And that's a valid equation. All of these xy points make that true. But it's not a function. Okay, if you wanted to graph this thing in a graphing calculator and you tried to solve for y, you would have to move the x squared over and square root both sides, but you would have to create two separate functions, the positive square root and the negative square root, because individually they're functions, but if you put them together, it's not a function. This is an example of y being defined implicitly, not explicitly. But I still want to be able to find the equation and the slope of the tangent line, such as this blue line shown. So we need to learn how to take a new kind of derivative for when we either can't or it's not convenient to get y all by itself. Okay, so here's an example. In this first equation, this is a quadratic equation. It's a parabola. Y is defined explicitly. That just means we know exactly what y is. If I substitute in an x, I do these operations to x and I get the value of y. In x squared plus y squared equals 25, y is defined implicitly. That means we still know what y is in relation to x, but y is not solved for, it's not alone on one side of the equation. It's kind of in the midst of the equation, and we kind of approach those in a different way. However, we still need to know how to find the derivative so we can know the slope of the tangent line. So that's what our instructions are going to be in this video. How do you find the derivative and get the slope of the graph if it's not solved for y? Alright, so a little background. Technically, whenever you do a derivative, the chain rule is always happening. Even in a simple derivative like the derivative of 3x plus 2, which is just 3, correct? Technically, the derivative of 3x plus 2 is 3 times the derivative with respect to x of x. But the derivative of x with respect to x is always just a 1, so we never bother to put this on there because it's just 3 times 1, which is just 3. Okay, when we do the derivative of tangent, the derivative of tangent is secant squared, right? It's secant squared x times 1, which is the derivative of x. So the chain rule always applies, but if the argument of the function or the subject that we are differentiating, if it has a derivative of 1, which x does, then we never bother showing that chain rule. Okay, so instead of now we're going to be coming across y's as part of our derivative taking process. So right here, this is another way to say this would be dx dx, the derivative of x with respect to x. If we come across a, quote, y part, meaning we're taking the derivative of something in terms of y, all we have to do is this little chain rule, this little dy dx gets multiplied by that part. All right, so we're just going to be inserting times dy dx if we're ever applying one of our rules to a y instead of an x. Then we isolate that dy dx and we're done. So let's see what that looks like. Alright, so here's our circle. It's radius 5 centered at the origin. I'm going to work my way across just taking the derivative of each part. X squared, the derivative is 2x. Now this was an x part. I've been able to take the derivative of x squared for a while now because it's x. I'm taking the derivative with respect to x. Okay, so that's fine. The derivative of y squared is 2y. However, since this was a y part, I'm going to multiply by dy dx. Alright, and dy dx is just another, it's the same as saying f prime of x or y prime or d over dx of whatever. This is another expression for derivative. So if I can isolate that dy dx, I'll be done. And then the derivative of 25 is 0, no matter what letter and what variable you're differentiating with respect to. So now I'm just back to algebra. I need to isolate dy dx. I'm going to subtract 2x from both sides and get negative 2x on the right. Then I'm going to divide both sides by 2y to get the dy dx completely alone. And if those 2's cancel, I just get negative x over y. And this is the first derivative that you have seen that not only depends on what x is, but also depends on what y is. So to find the slope, you have to plug in the x and the y coordinate. And if you think about the graph, that makes sense. Because if this is a circle with radius 5, and I'm looking, that tangent line I had earlier was at the point 3, 4, I can't just plug in x equals 3 and know that this is the tangent line we're talking about, because when x equals 3, I've also got another tangent line down here. So to differentiate between which one of those tangent lines we're talking about, I'm also going to substitute in the y coordinate, and I'm going to know the slope of the tangent line at that xy point. All right, but when you do implicit, don't be surprised if y is a part of your derivative statement. All right, so here's another example. It's quite a bit more involved than that last one. So overall, this is a sine, and we need to take the derivative of sine. And we know at this point that the derivative of sine of anything is cosine of that same thing. However, the chain rule now says I need to take the derivative of that inside stuff. Sometimes we call that u, and we're going to multiply this by the derivative of u. Okay, what's the derivative of 2x? That's 2. What's the derivative of negative 7y? Negative 7 dy dx, because that was a y part. Okay, that's kind of like a nested chain rule, but the second nesting part was just the dy dx. All right, the derivative of 7y is 7 dy dx. Okay, so then on the right, we've got the derivative of 16y, 16 dy dx. So sometimes you're going to end up with 2 dy dx terms, and we're going to need to isolate that by factoring. All right, so let's see how we can make this happen. Let's distribute this cosine to both of those. I think that's going to be our best bet, and I get 2 cosine of 2x minus 7y when I distribute it to the 2, minus 7 cosine 2x minus 7y dy dx equals 16 dy dx. Now if I move, I need to get all the terms that have a dy dx in them to one side of the equation. So I'm going to move this term to the right side of the equation and get 16 dy dx plus 7 cosine 2x minus 7y dy dx. So once you get every term that has dy dx on the same side of the equation, you factor that dy dx out. And I get 16 plus 7 cosine 2x minus 7y times dy dx. I factor it out and put it on the right for no particular reason. Could have gone on the left. Either way, I'm going to take and divide both sides by this set of parentheses. My final answer is 2 times the cosine of 2x minus 7y divided by 16 plus 7 cosine of 2x minus 7y equals dy dx. So we get this big expression for the derivative of our original relationship, and it involves both x and y. Make sure you don't cancel this cosine. I know it's tempting. You see it on the top and you see it on the bottom, but this expression on the bottom is an addition. You can never cancel just part of a binomial. So leave it like that. All right, it's kind of complicated, but that expression would give you the slope of this graph at any point. And again, look at the original question. Why did we need to use implicit? Because this original equation would have been really hard, if not impossible, to solve for y. To try to isolate that y, you've got 1 over here, 1 over here. It's probably not going to get isolated. Definitely with not any normal and easy ways. So we just use this new implicit differentiation. Here's a picture of that last one, that last relationship. I just brought this up to show you that they aren't all like circles and ellipses. They don't all have to be non-functions. This actually is a function. This passes the vertical line test, but it's just a function that is defined implicitly. It's defined in a weird way where we can't get y by itself. There's always going to be either a y on both sides of the equation or two y's on the same side, and it's not going to be able to be isolated. But we can still get an expression, that big expression we just got on the last slide, that will give us the slope of the tangent at any point that we want. All right, here's an example. This is another kind of conic section example. I believe this one is an ellipse that has been rotated because of this xy term. But I wanted to show you one like this with this xy term in it because it creates a lot of problems. The derivative of 2x squared, no big deal. It's 4x. When we go to differentiate the 4xy, x and y are two separate functions. Actually, I'm going to consider 4x to be a function and y to be a function. And you know what we have to do when we have two functions multiplied together. That's the product rule. So here's how that goes. I do first times the derivative of the second. So that's 4x, which is the first, times the derivative of y, which is 1 dy dx, or just dy dx. I'm going to call it y prime in this example, just to show you that y prime and dy dx are the same thing. They're interchangeable here. But this is first times the derivative of the second, d second, plus second, which is y, times the derivative of the first, which is 4. All right, that little product rule right there is often left out. Even after you get pretty good at this, it's easy to leave out. So if you have an x and a y multiplied together, those are separate functions. Do the product rule and remember your implicit. All right, so moving on to the 3y squared. The derivative of 3y squared is 6y times y prime. And the derivative of 10 is 0. So now I take all the terms that have y prime, and I'm going to leave them on one side, and I'm going to move everything else to the other side. It doesn't really matter whether I move them to the right or I move everything else to the right. In this case, I'm going to move everything else to the right. I get 4x times y prime plus 6y times y prime equals negative 4x minus 4y. And I just took y times 4 and called it 4y as I moved it to the right. Okay, and now I'm going to factor out the y prime, 4x plus 6y remaining equals negative 4x minus 4y. I'm going to divide both sides by 4x plus 6y. And that's my answer. These cancel. And as I write this final answer, I'm going to divide everything by 2. If you're going to divide one thing by 2, then every single part needs to get divided by 2. So that leaves me with negative 2x minus 2y over 2x plus 3y. Again, it depends on both x and y because this is not a function. It's an ellipse. It has points that are vertical of each other. So it depends on both x and y. You have to plug in the whole point, not just the x coordinate of the point. All right, so there's some implicit derivatives. Just remember to tack on a dy dx or a y prime whenever you're dealing with a y part. Isolate that dy dx, and then you're golden.